Ever since their first appearance in the fossil record, some 530 million years ago, arthropods, or joint-legged animals, have been virtually ubiquitous as the most species-rich animal group on Earth. They exhibit a diversity in form unrivaled by any other animal group and, among many others, include such familiar creatures as horseshoe crabs, scorpions, spiders, ticks, millipedes and centipedes, crabs, lobsters, pillbugs, butterflies, ants, mosquitoes, beetles, and the list just goes on. The photographs shown here show only a fraction of the amazing diversity arthropods have to offer. This unparalleled success is in large part due to the segmented construction of their bodies and limbs. Each of these segments can be modified separately for different purposes, allowing arthropods to adapt to almost every possible environment and mode of life. Modern arthropod limbs, in their most basic form, have two branches. Each of these branches is often highly modified or lost to cater for a specific function of that limb. For example, moving around, sensing the environment, breathing, mating, and so on. This image shows a small selection of typical two-branched limbs of some extinct Cambrian arthropods. One of the major questions is how these double-branched limbs evolved. Central to this and other questions about arthropod evolution is a long extinct group, the anomalocaridid. They first appear some 530 million years ago during a geologic period called the Cambrian. The youngest anomalocaridid known date back some 480 million years and lived during the Ordovician period. To our eyes, these animals look very alien. They have a head with a pair of spiny grasping appendages and a circular mouth surrounded by toothed plates. Their long, segmented bodies carry flaps that were used for swimming. Virtually all anomalocaridid were active predators, grabbing prey with their spiny head limbs. Our understanding of anomalocaridid has followed a rather tortuous path, with isolated body parts for a long time being considered to represent different animals. In 1892, the frontal appendages were the first anomalocaridid parts to be described. They were believed to represent the headless body of a shrimp. After his discovery of the Burgess Shale in 1909, Charles Doolittle Walcott collected more anomalocaridid parts. He described the circular, plated mouth apparatus as a jellyfish and the partial body as a sea cucumber. Other parts, belonging to different anomalocaridid species, were placed in various arthropod genera. These views remained largely unchallenged for more than 70 years. It was only in 1985 that my co-author, Derek Briggs, together with the late Harry Whittington, quite literally put all the pieces together after a painstaking study of all the available material, and published the first accurate reconstructions of the complete animal in a landmark monograph. Yet, anomalocaridid remained highly problematic creatures, and it would be almost another decade before they were finally recognized as arthropods in 1994. Here we can see recent reconstructions of two typical Middle Cambrian anomalocaridid, Herdia victoria on the upper right and P. toyanet horsty on the lower left. While our understanding of anomalocaridid has made great strides, several features of their anatomy remained problematic and poorly understood. One issue concerned the homology of the flaps. It was not entirely clear to what part they were equivalent in other arthropods. The other was the apparent total absence of legs on the trunk. This image shows two so-called gilled lobopodians from the early Cambrian. These are even more basal than anomalocaridid. They sit even further down the arthropod evolutionary tree. Gilled lobopodians have a set of dorsal flaps and below those a set of stubby ventral legs. Fusion of both structures led to the formation of the two-branched limb of later arthropods. The flaps of anomalocaridid were believed to be equivalent to the flaps of gilled lobopodians. It was supposed that anomalocaridid had completely lost their ventral legs as a result of their swimming lifestyle. Our discoveries, however, tell a different story. So, let's have a look at the specimens. This is the key specimen of our new anomalocaridid from the early Ordovician Fezouata biota of southeastern Morocco, shown in dorsal view. Its early Ordovician age makes it the youngest anomalocaridid known. The fossil is approximately 1.3 meters long, but about 10 centimeters are missing at the end of the body, and during fossilization the carapace was slightly rotated and displaced backward. Taking this into account, the animal in life would have been circa 1.6 meters long. Uniquely, this fossil is preserved in 3 dimensions. On the left, you have the positive relief part. On the right, the negative relief counterpart. The counterpart has been lit in such a way and mirrored to give the false impression of positive relief, to make it easier to compare part and counterpart. On the left side, the flaps are revealed. Critically, there is a small separate block which sits in between the part and the counterpart. We are now going to move this block from the counterpart to the part. Pay close attention to the left side of the specimen. When we move the block over, a second set of flaps is revealed, dorsal in position to the flaps visible in the previous image. To clarify things a bit more, the image on the left shows the part with the rock surrounding the dorsal flaps digitally removed, so that both sets of flaps are visible in the single image. On the right is an interpretative drawing. Note the ribbon-like structures on the back of the animal. These are gills. Originally, they were believed to attach to the back. However, we were able to show that these structures in fact attach at the base of the dorsal flaps, being strung over the back between the flaps. In effect, these gills are part of the dorsal flaps. Also note the huge central element of the carapace, colored purple in the drawing. In life, this carapace element would have extended in front of the head. We'll take a closer look at the carapace shortly. This is a side view of the same specimen. Note the three-dimensional preservation and the lower ventral set of flaps. We can now digitally add in the dorsal set of flaps from the counterpart. As you can see in this image, both sets of flaps are separate from each other. And this is more clearly shown in this interpretative drawing of the specimen. After the discovery of a second upper set of flaps in a new Moroccan fossil, together with my co-authors Alison Daly and Derek Briggs, we revisited the older Cambrian anomalocaridid's Peabody nat horsty and Herdia victoria that had been described earlier. As you can see here, Peabody nat horsty also shows clear evidence for the presence of two sets of flaps. These had been misinterpreted or overlooked in previous studies. Herdia also shows evidence for the presence of two sets of flaps. Returning to our Moroccan fossils, we'll now have a closer look at the head. The head is covered by an elaborate carapace consisting of three elements. In this image, you can see the elongate, pointed central element. This element extended in front of the head and accounts for approximately half the length of the animal. The biggest central element collected to date measures approximately 1 meter and 5 centimeters. This means that the animal reached a gigantic size of at least 2.1 meters, making it one of the largest arthropods to have ever lived. It was also by far the largest animal in the Ordovician seas. This photograph shows one of the rounded side elements of the carapace flanking the central element on each side of the head. There is still a fragment of the central element visible on the right side. We can remove this central element to completely uncover the lateral element. Note the upturned protrusion on the lateral element. This is all better visible in the interpretative drawing. Here we can see the frontal appendages of the new anomalocaridid. The actual appendage is rather short and fat. Each segment carries an exceptionally long spine on its lowest side. Now, let's zoom in a bit on those spines. In this close-up, we can see that the ventral spines carry an array of flexible, mobile spines on their front margin. These mobile spines insert into sockets. On the upper edge of the mobile spines, they have a double row of minute, densely spaced fine spines. The red arrows point to places where the double row of fine spines is visible. This delicate and intricate construction of the frontal appendages is unlike that of any other anomalocaridid. The spines on the appendages would have formed a fine sieve or net, allowing the animal to filter plankton from the water. This is in contrast to virtually all other anomalocaridid's, which were active predators. This is another specimen of the frontal appendages of the new animal. Note the extreme length of the spines coming off the appendage segments. We can now make an accurate reconstruction of our new anomalocaridid, as shown in this fabulous rendering by Marion Collins. Note the large three-part carapace covering and extending in front of the head, the elaborate filter-feeding appendages, the flat, broad trunk, the two sets of flaps on the side of the trunk, and the gills on the back, which attach at the base of the upper flaps and are stretched across the trunk. We decided to name the new animal Aegirocassis benmoulae. Aegir is a giant and ruler of the seas in Norse mythology, and this part of the name reflects the massive size our animal attained and the fact it would have been unassailable by any other creature in the Ordovician. Cassis is Latin for helmet and is a reference to the elaborate three-part carapace covering the head of the animal. Finally, benmoulae is in honor of Mohammed Usaid benmoula, the man who collected the specimens used for our paper and who discovered the exceptionally preserved Fezouata biota the new animal belongs to. Aegirocassis benmoulae offers several major new insights. First, it resolves one of the most problematic aspects of anomalocaridid anatomy, the supposed absence of limbs. Our specimens show that not the lower flaps, which were previously known, but the newly discovered upper flaps are equivalent to the upper flaps of the gilled lower podians we saw earlier. This means that the lower flaps are, in fact, modified legs. Hence, anomalocaridid's didn't lose their legs, they transformed them into flaps for swimming. From this follows that the flaps of anomalocaridid's are equivalent to the upper and lower branches of the later double-branched arthropod limb. The fact that they are still separate, unfused structures in anomalocaridid's shows that they occupy a very early stage in the evolution of arthropods, before the fusion of both structures into a double-branched limb had occurred. The discovery of Aegirocassis benmoulae is also significant from an ecologic point of view. While almost all other anomalocaridid's were active beasts of prey who grabbed their quarry with their spiny head limbs, the Moroccan animal had its head appendages modified into a very intricate sieve, allowing it to filter plankton from the oceans. Aegirocassis benmoulae attained a massive size of at least up to 2.1 meters in length, ranking it among the biggest arthropods to have ever existed. This giant evolved during the early phases of a massive increase in biological diversity, known as the Great Ordovician Biodiversification Event, which also shows a sharp hike in plankton diversity. In this way, Aegirocassis benmoulae foreshadows the appearance under comparable conditions of giant filter-feeding sharks and whales in much more recent times. As such, the Moroccan fossils provide by far the oldest example of an apparently overarching trend of massive plankton-eating animals evolving from active predators at the time of a large-scale increase in plankton diversity.
To conclude, a quick visit to the key specimen in the collections of the Yale Peabody Museum of Natural History. What I want to impress upon you is the sheer size of this animal. This specimen is approximately 1 meter 30 long. However, first of all, there is a small bit of about 10 centimeters missing here at the back. In addition, the carapace at the front, during fossilization, has been rotated slightly and pushed backward. If you take that into account, this animal, while it was alive, would have measured approximately 1.6 meters long. Now, this is by no means the biggest individual of Aegirocassis. We know that the biggest animals got up to at least 2.1 meters. Now, I want you to consider this. 2.1 meters. That is actually taller than a standard size door in your house. This means that if you would have taken a big individual of Aegirocassis, you would have put it on its tail. It would have been unable to fit through your door. So this animal, by any standard, was